So today we have two-page replacement algorithms and basically what is need of that. And before that we'll discuss few things. So first one is copy on write. In short, it is called as COW or maybe cow also. Okay. So copy on write. This technique allows both the processes to initially share the same pages in memory. Now, reason why we do so is, if you look it carefully, whenever we make use of fork system call to create the child process, remember that a duplicate process will be created. Okay, so fork creates duplicate process, that is a child process for the parent process. Now, when we create a duplicate process, a parent process has some sort of, say for example, 8 pages or 8 frames allocated to it. Now, for a child, again, we need 8, even though it is a duplicate, right? So, to make fork work fast, this technique is used, that is cow, copy on write, which allows both parent and child process to initially share the same pages in the memory. Because this is a duplicate process, whatever 8 frames are there, 8 frames will be used by both the parent as well as by child. Okay. And then if either process modifies the page, whichever page is there, if that is modified, then and then only copy of that will be created. Say for example, process 1 has 3 pages, process 2, which is a duplicate of process 1, again has 3 pages. Now in physical memory there will be only 3 pages that will be shared by both process 1 and process 2. Okay, but now when process 1 or process 2, whichever process modifies that time OS will create another frame. So copy on write. Write is what the modifications are. So this write refers to modification. So if any process makes modification, then a new copy of that frame will be created. Okay. So this is really very efficient method of process creation, as only modified pages are copied, and because we are sharing the same pages, this results in very fast creation of a child process. Now, whenever we allocate the free pages, we know that we need to keep track of how many pages are free or how many frames are free, right? So for that, there will be separate thing called as pool of free pages. Okay. Another word used for that is zero fill on demand pages. Okay. Where the pool always have free frames for fast demand page execution, rather than searching which frame is free and which is in use. You have a list of free frames, so no need to execute some sort of a searching algorithm there. Okay, and based on that, another variation of fork, that is called as vfork, that is available, in which what happens is it will suspend the parent and child makes use of copy on write. Okay, this is especially designed to make use of exec in the child process. Reason being, we already implemented one of the small application of shell, where we create a child process, and whatever the command given by the user, that will be used to locate the executable file, and some exec calls are there that will load into the new, that is the child process. So in this situation, copy on write is very efficient mechanism. Okay, so let us see one example. Suppose process 1 is there, process 2 is there, 3 pages are shared between process 1 and process 2. So in physical memory, actually process 1 has 3 and process 2 has 3. So total 6 pages should be there, because we always say each and every process has its unique memory. Okay, but even though it is unique to that process, in order to save the memory, physical memory, sharing, even in case of segmentation, even in case of paging, we studied that part, right? Now here we want to just see copy on write. So suppose, for example, in this case, this is the situation where 3 pages are shared between process 1 and process 2. And now assume that process 1 modifies one page. Let us call page C is modified by process 1. This C is modified. Now those changes should not affect the process 2, because process 2 want to continue with its original contents of process C. Now this time what operating system does is copy C into another frame. That is what copy on write is. So for example, page C is copied here. So new frame is allocated. Now process 2 will continue with original contents, and process 1, which modified page C, will continue with latest contents for that process. This is called as copy on write. This is called as copy on write. Now every time we see whenever page fault occurs, or whenever copy on write kind of thing is there, whenever in any reason, whenever process needs some sort of a frame, so that page will be loaded into that. What will happen if there is no free frame? Okay, that means my memory is full. So we already discussed this part in case of the segmentation, or even in case of paging also, wherein whenever there is no space in the main memory, we try to utilize the backing store, that is the swap space. That is the swap space. That means we need to select some sort of pages from main memory and take them out on the swap, that is a page out, and whichever page you want to load for that frame will be available. Okay. So there are few questions, like in this case, how much to allocate to each process. Okay. Now if you want to do some sort of a page replacement, okay, page replacement is what? Taking page from main memory to backing store, that is page out, and whatever the desired page is there, take that in. And there are so many algorithms for that. Anyway, that we'll discuss in today's session. Okay. So now how this algorithm works. Anyways, we'll see, and what is the performance of that algorithm. Right. So we'll go with page replacement algorithms. The same page may be brought into the memory several times. That is basically related to the concept of some sort of thrashing. That also we'll discuss with one of the case. Okay. So page replacement will try to prevent over allocation of memory by modifying page fault service routine to include page replacement. So one of the basic goal behind this page replacement is to reduce the page fault rate. Okay, so that is one thing. The second thing is it will try to utilize something called as a dirty bit. Most of the text makes use of the word dirty bit. This textbook makes use of modify bit. Because whenever we say when we want to move the page from main memory to the backing store, in demand paging we already studied that actually page is loaded from backing store into the main memory, right? So contents are already there on the backing store, and if it is not modified, we can save disk IO time, because originally page is available on backing store, that is copied into one of the frame. Now suppose that frame has to be replaced with another page, maybe because of page replacement or because of that process needs something free frame. In that case, we need to write the content of that frame back to the backing store. But if it is not modified, then no need to transfer the contents. So one simple bit is utilized for that, stating that whether that page is modified or not, so that only modified pages will be written back to the disk. So that definitely saves some sort of time. Okay. So this page replacement completes the separation between logical memory and physical memory. Yes, that is actually happening because of this virtual memory. So large virtual memory can be provided on even smaller physical memory. So that is one of the again advantage of this page replacement, because virtual memory concept we studied, but in order to implement that virtual memory concept, page replacement is the major backbone behind it. Okay, so let us see first upon the need for it. If you look this diagram, total 8 frames are there in physical memory. So concentrate here. Total 8 frames are there. Out of these, 2 frames are used by the operating system. So only 6 are remaining. Now there is, say for example, process 1, which needs 4 frames. There is another process, or you call it as a user, which needs 4 frames. So the page table for first process is given there, where the content H, so 0, 1, 2, 3, 0, 1, 2, and 3. First 0, 1, 2. First 3 pages have been loaded at the location frame number 3, 4, 5. So this H is loaded here, load M is loaded here, J is loaded here. Note that M part, that is the 4th page of process 1, is not loaded. So valid invalid bit says it is I, invalid. It is not loaded there. And same is the case for second process, where A, B, D, E, 4 is the requirement, but 3 are loaded, and the page with contents B is not loaded. So its flag is invalid. Why it is not loaded? Because there is no space, right? There is no space. My physical memory have limited frames. So 6 frames are available for user processes. Now first process occupied 3, second process occupied 3. Now for example, load M, this is available on backing store, and this B, this is also available on backing store. Okay. Now, if we want to load, say for example, in process 1, the program counter is now pointing to load M, which is not loaded actually in the memory. So I need to replace one of the page so that, sorry, M page is not there. M page is not there. Let us assume that we want to execute this part, B, page number 2 from process 2. That means we need to take this page B from backing store to physical memory, right? but there is no free frame there. Whatever 8 frames are there, they are all full. So there is no free frame. Getting it now? That means we need to select one of the frame from 2 to 7. Take that frame in one of the backing store page. Make free frame available in the main memory. And then from backing store to main memory, we need to copy the contents of page B. That is the need for page replacement. Very simple thing, a small amount of physical memory and very large amount of virtual memory. If some processes need some X amount of pages, we can start that process without loading all X. Few pages could be loaded and it will start its execution. But whenever it comes across a page which is not loaded, it results in page fault, memory management unit sensor trap, and then operating system will try to find out free frame. And if there is a free frame, no issues. But if there is no free frame, then page replacement algorithm is required. Then page replacement algorithm is required. Now there are so many questions. If I want to load B into the memory, which page I should take out of main memory? Whether it should be from the same process or from other process. Okay, so those basic page replacement things are required. So whenever you need page replacement, first upon you need to find the location of the desired page which you want to brought into the main memory on the disk. So find out on disk first of all that page which you want to take into the main memory. Now look at the main memory and find a free frame. If there is a free frame, use it, no problem. So simply the page from disk will be copied into the free frame. But if there is no free frame, then you need to call the page replacement algorithm, and for which you need to select the victim frame. Okay. Now victim frame, which victim frame you will select? From the same process, from other process? Okay. Now whatever the victim frame you have selected, if dirty bit of that is set to 1, that means that frame is modified, then 2 write operations are required. One is whatever the selected victim, you need to write it back to the backing store, number 1. And then whatever the desired page you selected from the disk, you want to take that into the main memory, again you need to copy. So 2 disk IO operations are required. So again very simple thing. If you want to increase the performance of this, while selecting victim itself also we can play a trick. If we select a victim such that dirty bit is not set, then we can definitely save 1 disk operation. Okay. So that is step number 2. Step number 3 is bring the desired page into newly free frame and update page and frame tables, because previously it was invalid. Now copy it. Once that copy is completed, mark its flag to V, saying that it is valid. Okay, and continue the process by restarting the instruction that calls trap. Yesterday we saw the 12 steps for that, if you remember. Okay. Okay. Within frame 30 bit set, now there is potentially 2 page transfers required for page fault, and that will increase effective access time. Okay. So the same thing is depicted here in the diagram. Something like this. The frame number 0 and F is given there, considering this as a hexadecimal number, and F, it was valid previously, but now that was selected as a victim frame. So we need to copy this victim to backing store. Whatever the desired page is there, that will be taken in. Okay. So now steps important. Step number 1 is victim will be swap out. Now because that is swap out, we need to modify its valid invalid bit, because now that is not available there, right? Then whichever is the required or desired page will be swapped in, and for that page again we'll modify the valid invalid bit. That means previously desired page was not there, so its valid invalid bit was set to I. Okay, because now it is copied into the physical memory, now we need to modify it to V. That means it is valid. Now the algorithms we want to see: the frame allocation algorithm and page replacement algorithm. 2 types of algorithms are there, where frame allocation algorithm will determine how many frames to give each process. There is settle for that. As I mentioned, if we have a 3 byte instruction where each and every byte is available at different pages, so at least 3 pages are required for that case. So it all depends on what kind of processor you are using and the longest instruction set required for that, number of in terms of number of bytes, and then which frame to replace. Now let me tell you interesting part. Suppose if I have a 3 byte instruction, okay, and if just 2 pages are allocated to each and every process, just 2 pages, and 3 byte instruction is there where all 3 bytes are referring to different pages. So first byte is available, second byte is available, that is okay. Now for third byte it will result in page fault, and if we decide to only select the victim from the same process, what will happen? Either first page or second page will be swapped out, third will be taken in. Suppose first is swapped out, third is taken in, the instruction will be restarted, and when instruction is restarted, again we are in need of first page. So in order to take first page in, maybe we'll replace second or third. So second is replaced, so next part of the instruction needs second page. So that means your system will only be busy in page replacement and not doing any actual thing. Now, this concept is actually called as a thrashing, that we see. So that means we need to calculate the minimum number of frames that should be allocated. Okay. So for example, if the minimum number of frames, for that you need to talk about the hardware architecture. Okay. Just a minute. So that is frame allocation algorithm, and second part is page replacement algorithm. We want page replacement algorithm such that it will result in lowest page fault rate on first access also and re-access also. And because multiple algorithms are possible, we need to evaluate algorithm. And for evaluation, the most important thing is we need to go with some sort of a reference string. Okay, so reference string is created just by taking list of page numbers. Okay, it is just page numbers and not full addresses. So for example, page number, if you see it here at the bottom here in red color, 7, that means my process needs page number 7, then my process needs page number 0, then my process needs page number 1, then 2, then again 0, then 3, then again 0, then 4, then 2, then 3, something like this. Okay. So whenever we make use of, actually it is a shortcut we created. So for example, if some address is there that is loaded into the program counter. Okay. So let us assume that the address is something like 0x1249, 0x1249. Now in this address we have some sort of page number and the offset. That part we already discussed in case of a paging, where page number is P and offset is D, right? Now whatever that page number, just that page number is taken here as a decimal. Okay, and collection of such page number is called as a reference string. So that means for that particular process needs pages in this particular order. Okay. Now it again, let me clear one thing. This doesn't mean, like for example, in the example given here, the first part is 7 and next part is 0. That doesn't mean first instruction is from page number 7, second instruction is from page number 0, third instruction is page number 1. No, it's not like that. Okay. Repeated access is simply removed. So for example, if size of my page is say 50 bytes, maybe 50 instructions are there, or data is there, or data and instruction. It's a combination of both. Okay. So it starts with, say, main function starts with on page number 7. So page number 7, first instruction, page number 7, second instruction, page number 7, third instruction, page number 7, fourth maybe data, then 5, 6 up to 50. And then what is required is page number 0. So repeated access to the same page actually does not cause the page fault. So repetition of this frame is simply removed. It is just removed from that, right? So that is what the reference string is. Now what we expect is something like this: the number of frames allocated to that process versus number of page faults. This is quite obvious. As you increase the number of frames allocated to that process, that means many pages of the same process will be available in main memory, and because that is available in main memory, it will result in less number of page faults. So that is the relationship between the page faults versus number of frames. Okay. Any doubt in this? Try to understand, because based on this there is one anomaly, Beladi's anomaly, that we want to discuss. But this is very simple thing. Do you have any doubt? If there is any doubt, please put it in chat box. Page fault versus number of frames. Why it is so is very simple thing. If just 2 frames are allocated to your process, now the graph actually starts with 1. So if only 1 frame is there, whenever you change the page, it results in page fault. Okay. Fine. Now let us start the algorithms. Very first algorithm is FIFO algorithm. First in, first out. As the name suggests, whichever page loaded first will be taken out. Now let us see the example here. Assume that this is the reference string, okay, and we'll assume that for a particular process 3 frames have been allocated. That means maximum 3 frames in main memory will be available at a time for that process, right? So initially all these 3 frames will be empty, and this is as per pure demand paging. Page will not be loaded into the memory until it is required. So we'll assume that initially all 3 frames are empty. Now the process execution starts and it referred first instruction out of that, and it is coming from page number 7. So first upon 7, so this will be loaded into the main memory. That means one page fault occurred. Process starts its execution. It refers page number 7. Page number 7 is not in main memory, so page fault has been occurred. So once page fault occurs, what happens is it will load the page from disk to the main memory. That means one page fault occurred here, right? And that is loaded in one of the frame. So it is loaded here. Now next is 0. That is also not there. Now this is the current situation where frame number 7 is valid, next frame is invalid, next frame is invalid, and only 3 frames are there. Now 0 is also not there. So that results in page fault that will be loaded here, right? Same thing happens here for page number 1. It is also not available because 7 and 0 is only available and 1 is not available. So 1 is loaded here. So how many page fault occur till now is 3. Okay, now what's page number 2? Now page number 2 is not available. Currently, what is there in memory? Page number 7, page number 0, and page number 1. So page number 2 is not available. And if page number 2 is not available, that resulted in page fault. Now that must be loaded into the main memory. But while loading into the main memory, there is no frame available because maximum 3 frames are allocated to each and every process. And all 3 are already utilized by this process. One with page number 7, another with page number 0, and third one is with page number 1. When I say page number, remember it is from virtual memory. And when I say frame, it is physical memory. So 7, 0, 1, 3 are already full. That means now we need to select the victim. Either 7 or 0 or 1 we need to replace, right? So we need to select the victim. Now which to select? Now because we are discussing first in first out, that is FIFO algorithm, out of 7, 0 and 1, which one is loaded first? It's 7. So frame number 7 will be selected as an victim, remember. And then at the place of 7, here you can see at the place of 7, page number 2 is loaded. But again, remember, we need to count this as the page fault, right? Now next is what? 0. And 0 is already there, no? 0 is already there. So that means there is no page fault. OS tried to access this 0th page and it is found in the main memory. So it is simply access. There is no page fault. Then 3. See, it was initially 201. 3 is not there. That means we need to remove. Now what to remove? Out of 201, which one is loaded first? 0 is loaded. So 0 is replaced with 3 here. This is one more page fault. Now it refers to 0. Again there is page fault. So out of 231, 1 was loaded first. So 1 is replaced with 0. So this is again page fault. 4, yes, this is page fault. Just continue with the same thing. 2 is page fault, 3 is page fault, 0 is page fault. At this time, 0, 3 is there. 3 is there, 2 is already there, so no page fault. 1, yes, it results in page fault. 2, yes, it results in page fault. 0, no page fault because 0 is already there. 1 is already there. 7, it results in page fault. 0, yes, it results in page fault. And 1, this again results in page fault. So how many page faults are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are total 15 page faults are there. Okay. And if you think of how many non-page fault pages reference are there, 1, 2, 3, 4, 5 are there. Okay. Any doubt in this? Any doubt? Or somebody should respond. If you understood, no problem. Just reply with no problem. And if you need any explanation, then you ask your question. "91 participants are there." Okay, no doubt. Fine. So this is very simple thing. The page which is loaded first will be selected as a victim. That is the punchline for this FIFO algorithm. Okay. So how to count the page faults? That is important. Okay. Now there is something called as Beladi's anomaly. See, because we studied it for 3 frames. Now you can solve the same example for 4 frames also. So definitely, as we have increased the number of frames, it should decrease the number of page faults. That is what we studied in previous slide. In this graph, as you increase the number of frames, it should decrease the number of. So meaning of this is, for example, in this case, if number of frames are 2, number of page faults are 7 here. If you check it here, if the number of frames are 3, number of page faults are 5. So here it is 7, here it is 5, here it is 6. Approximately I'm taking actually. And here it is 4, something like this. Sorry, it is 4 here. It's actually 4 point something, but let us think like 4. Whereas what Beladi's anomaly says that there is a situation which will cause more page faults if you add more frames. So this is actually contradicting our previous diagram. For that, this is the example. Like for example, this is the reference string, and for this reference string, if you go with just single frame, it will result in 12 page faults. With 2, it will result in 12. With 3, it results in 9. that is okay. Up till this now it is okay. But if the number of frames are 4, it results in 10 page faults. Okay, that is called as Belady's anomaly. What is Belady's anomaly? Increasing number of frames, sometimes I am saying sometimes, results in increase in page faults. Okay, that was the FIFO algorithm. Next one is, so I can say that was a problem with FIFO algorithm. So optimal algorithm, this is the second algorithm. What it says is replace the page that will not be used for longest period of time. That will not be used for longest period of time. That means you need to look for the future. So for example, here let us try to solve the same example with the same reference string with number of frames equal to 3, and then we'll calculate the number of page faults, right? So 7 is first page fault because initially all page frames are empty. 7 is loaded, 0 is loaded, 1 is loaded. So 3 are definitely 3 page faults are there. After this 3, the page frames will have 3 pages, 7, 0 and 1. Now the next thing is 2. Now we want to load 2, but there is no space or there is no frame which is free. Now out of 7, 0, 2, which one to replace? Now optimal algorithm says that select the victim based on what? That will not be required for longest period of time. So for example, when 7 is required, if you consider this as increasing time, if I consider this as a time, 7 is required somewhere here, right? 0 is immediately required. Out of 7, 0, 1 I am talking about, and 1 is required somewhere here. So these are all future references. How do you know about this? This is really the difficult task, and that is the reason optimal algorithm is used just for measuring how other algorithms are performing. Why this is not implementable? Reason behind that is very simple. We never know which frames will be required in future. Because conditional, unconditional branches are there. Few pages are required depending upon if else, which function is called, something like that. Okay, so working of this algorithm is very simple. 0 is immediately required. Say out of 7, 0, 1, 7 is required at this point of time, 0 is required at this time, and 1 is required at this point of time. So longest period, 7 is not required. So 7 will be replaced with 2. 7 will be replaced with 2. So this is also a page fault. This is also a page fault. Now next one is what? 0. It is already there. No problem. Then what is next? 3. So 0 is finished. Now at the time we need page number 3. What we want to do is, now 3 is not available, resulted in page fault. So we need to remove out of 2, 0 or 1. Again the same thing. What I'll do is, let me delete this one, and this one. Assuming this is a timeline again. Okay, 2, 0 and 1. 2 is required here, 0 is required here. So longest period of time 1 is not required, right? So 1 will be replaced with 3. See here, 2 and 0 is same. Okay, so for 3 also there is a page fault. Now having this 2030, yes, it is already there. No problem. What about 4? Now there is 2, 3, and 3. 2 is immediately required. After that 3 is required. So definitely 0 will be replaced with 4. So this is one more page fault. Now 2, yes, it is already there. So no page fault. So for 0 also there is no page fault. 3, no page fault. 0, yes, 0 is not available there. 2, 4, 3. Now 3 is there, 2 is there. Definitely it will replace 4 with 0. So this is one more page fault. So on, so forth. So 3 is already there, 2 is already there, 1 is not there. So out of 2, 0, 3, 2 and 0 are immediately required. So it will replace 3 with 1. So this is page fault. 2 is already there, 0 is already there, 1 is already there. For a 7, there is a page fault, so it will remove 7. 0 is already there, 1 is already there. So with same number of page frames, that is equal to 3. With optimal algorithm, how many page faults are there? It is 1, 2, 3, 4, 5, 6, 7, 8, 9. Just 9 page faults are there. Versus with FIFO, it resulted into 15 page faults. So definitely optimal algorithm gives some good value with respect to number of page faults. The next algorithm is least recently used, that is LRU algorithm, which makes use of past knowledge that is available. See, future knowledge we don't have with us, but past knowledge is with us. So it will make use of past knowledge rather than the future, and it will select the victim based on the page that has not been used in most amount of time. So the page which is not least recently used. Let us see it. 701. This is same thing for all 3 algorithms, because initially all page frames are empty. So definitely first 3 will result in page fault. So 3 will be loaded there. Now out of 701, we need to select victim for loading page number 2. So in optimal, we move time that is in the history, something like this. Now arrow is in this direction. Now out of 701, which is least recently used, that means which is not been used in most recent amount of time. Most recently used is 1. Before that 0. Before that 7. Right? So 7 will be selected as a victim, and that will replace with 2. So this results in page fault. 0, it is already there. Now 3, yes, this is page fault. Now for 201, which one is selected? 0 is most recently used. Rather I can say it is recently used. Then 2 is used, and then 1 is used. So 1 will be replaced with 3. 0 is already there. 4 results in page fault. So out of 203, 0 and 3 are used, 2 is not used, so on so forth. Okay, now 2 is already there. 1 replaced here. 2 already there. 0, yes, it is not there. So 3 will be selected as a victim. 1 already there. 7, no, it is not there. So 0 and 1, they are already there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 page faults are there. Okay. There will be 12 page faults. So definitely this is better than P4, but not like I can say worse than OPT, that is optimum page replacement. So this is generally good algorithm, and most of the time this is used. But then for LRU, the thing is how to implement it. FIFO fine, FIFO can be implemented by simple queue. How to implement LRU? So for a LRU, maybe different kind of counters are used. So one of the solution is by making use of counter, where every page entry has a counter. Every time page is referenced, through this entry, copy the clock into the counter. So that is one of the solutions. That means we are keeping track of time, and the older page will be simply replaced. Stack implementation is possible, where we'll make use of stack of page number in double link form. Whenever page is referenced, we'll simply move that page to the top. Of course, if you want to implement this stack with double link, you need to modify 6 pointers. Okay. Advantage of this is whichever is at the bottom of the stack, that will be replaced. So there is no search required for replacement. Remember, LRU and OPT, these are stack-based algorithms, and they do not have some sort of Beladi's anomaly. Beladi's anomaly is only possible, only problem with the FIFO algorithm. Right? Now, how this stack is used, one small example is that if this is a reference string, stack before A is something like this, where 2, 1, 0, 7, 4. That was the condition of stack. Whenever you refer 7, 7 was previously here, no? So 7 will be simply moved from this location to the top of the stack. Same thing is here. So it starts like 7, then 2, then 1, then 0, and then 4. That is how to make use of stack. I think we are running out of time, so let us stop here.